Um, this hill, the top of that hill, is the quote-unquote transition state. So this represents a collection of atoms and electrons that have kind of been slammed together. The electrons have been displaced on some level from their normal positions before in the reactants before the reaction went forward. And this is some high potential energy state, right? You've had to deliver potential energy to these electrons to move them out of their bound position. If you want to get this reaction to move faster, the best thing that you can do for it is to make this species, whatever this entity is, be lower in energy than it is in the uncatalyzed reaction. So how do you make charge distributions be low energy? You're low energy when you have oppositely charged species close together, right? Keep going back to this over and over again. If you can bring positive charge and negative charge close together, you're lowering the energy. You're lowering those electrical potentials, right? Now, a catalyst, essentially, many catalysts essentially go after that. They try to find conditions in which this hill, whatever the species is that exists at the top of that hill, is lower in electrical potential than in the uncatalyzed reaction. If that's the case, if they can figure out a way to do this, then to get here, you don't have to put as much energy in. Let me show you a way that this can be done. I'm not going to talk about specific reactions. I'm going to be very generic. But imagine this for a second. This is just a big blob. But imagine that this is your transition state. Somehow, you've got 3 different atomic centers, and you've smashed them together. And in the transition state, one of those atomic centers has a 2+ charge on it, and 2 of the other centers have a 1- charge on it. So this is a neutrally charged intermediate, or not intermediate, transition state. You need to get this distribution of charge across the molecules. Well, imagine this happens this drawing is not showing up the way it was supposed to. Imagine that happens inside a pocket that has charged species available to surround this with. Well, if in that pocket, the catalyst, maybe it's an enzyme catalyst, this is how a lot of enzymes function. If the catalyst can provide a positive charge in close proximity to where the negative charge needs to build up in the transition state, and if the catalyst can provide negative charge in close proximity to where the positive charge builds up in the transition state, then this species will be at lower energy when it's bound to the catalyst than when it tries to exist on its own, correct? And so on some level, what a catalyst's job is to do is to find a way to lower the electrical potential energies of transition states. If it does this, it brings the energy of the transition state down, and therefore the activation energy, we'll call this the activation energy of the catalyzed reaction, decreases. If the activation energy of the catalyzed reaction is lower, then the reaction proceeds more readily because a larger number of the collisions have sufficient energy to get you over the smaller hill. Does that make sense? So I've drawn a little map down there that shows in the uncatalyzed reaction you have a big hill to climb, and in the catalyzed reaction you've got a small hill to climb. One other kind of a catalyst. Example of catalyst. This one isn't very specific in terms of electrostatics, but in this case, what the catalyst does is it provides a new intermediate that's higher in energy than were your reactants, but has a smaller hill to climb to get to. So in the uncatalyzed reaction, you have the reactants just by themselves trying to get the products. In order to get there, they've got to proceed through this really high energy transition state. In the catalyzed reaction, the reactants in the place of the catalyst have the ability to become something else, some other species. Catalyst bonds to reactants, they become this other species. The hill they have to climb to get to that other species is lower than it was in the uncatalyzed reaction. And then once they get to that intermediate, they only have a very small hill to climb to move on towards products. Well, because in this reaction, we only have two small hills to climb versus one really big hill, it proceeds a lot faster. And this second reaction that proceeds decomposes that intermediate to give you products and the free catalyst back. And so the catalyst has done its job in that it wasn't consumed in the reaction. It was consumed momentarily in one step when you form this intermediate, but in that second step it got regenerated. We'll be working with problems in our homework where we show the catalyst doing just that, reacting in one step and then being consumed in the second step. All right, so just a quick summary of what we just talked about. Again, you don't need to know, you don't need to work or be able to work with the actual rate equation, but you do need to understand the dependencies or the dependencies on the variables that you find in the rate equation. So you got concentration dependent terms. Obviously, if concentration increases, your number of collisions in the system are going to increase and your rate's going to increase. And so that's why we've got these terms here. You got your K out in front of those concentration terms. Your K is equal to A, e to the negative E sub A over RT. The E sub A term here describes the activation energy of the reaction. Your temperature term in the denominator accounts for the rate increasing when temperature increases. And your A term in front of the exponent, the quote-unquote pre-exponential factor A, is a function of those geometric constraints on collisions. To another kind of big subject, big topic that derives from the conversation we just had. In some reactions, when products are made, they remain kind of trapped in whatever volume the reaction originally occurred in. And so as the reaction proceeds, the amount of products build up. For these systems, if the products have a mechanism for moving the other direction on the reaction coordinate. So we can go from reactants to products, and we can go backwards from products to reactants. If we can do that, then your system is going to achieve a state of quote-unquote equilibrium. What this equilibrium is it's a position in the reaction, in the course of a reaction, where the rate at which products are made by reactants is equal to the rate at which reactants are made by products in the back reaction. Okay? So these special kinds of reactions, these equilibrium reactions, you can move forward and back. If that's the case, as the reaction begins proceeding and concentrations of products begin to build, the rate of the back reaction is going to increase. Rates are a function of concentration. And so as the forward reaction increases, building up the concentration of the product species, the back reaction will increase, creating the reactant species. Let's take a hypothetical reaction where you have A molecules and B molecules in equilibrium with C molecules and D molecules. The definition of equilibrium is that the forward rate and reverse rate are equal. So you can write our mathematical expression for the forward rate, assuming that this is one elementary step in this reaction. Then your A molecules are going to have a coefficient of 1, your B molecules are going to have a coefficient of 1 in the rate law. You're going to have your K for your forward reaction. This is going to be equal to the reverse rate. You'll have your K for your reverse rate. Concentration of C molecules and D molecules or coefficients would be 1 if only one C and D molecule are involved in the reaction. We're going to do a little bit of algebra, and we're just going to take all of the concentration terms, stick them on one side of the equation, and we're going to take the K terms, stick them on the other side of the equation. Now, we said that the K's were A for the reaction, and then e to the negative e sub a over RT. Right? So you have one K for forward direction. It'll be A forward, e to the negative, activation energy forward over RT. You'll have K for the reverse direction. It'll be the A for the reverse direction, e to the negative e sub a over RT, where that's e sub a over the reverse reaction. Now notice that everything over here is a constant. The activation energy, it's a constant. It's a function of the exact kind of electronic state that you got to put those electrons up to before the reaction will occur. And so E sub A is constant for the forward direction and the reverse direction. Your A values, those guys are constant, right? Because they're a function of the exact geometric parameters. Temperature, if you're at a single temperature, your temperature is constant. Everything in here is constant. It doesn't change. Well, what that implies then is that the ratio of the concentrations to the powers of their coefficients is also a constant. And that leads to, the fact that that's a constant, leads to predictable behavior from these systems that are in equilibrium, particularly when equilibrium is disturbed. A quick note, just based on the value of your K constant. K is equal to the concentrations of the products raised to their coefficients over the reactants raised to their coefficients. If you have a K value, an equilibrium constant for a system that is much larger than 1, I got my direction on these dashes backwards. So if, no, I didn't. Okay, so if your products are favored, K is going to be much, much larger than 1. If your reactants are favored, K is going to be much, much less than 1. Now let's look at how K, or how systems respond to changes in equilibrium. So start off at equilibrium. At equilibrium, your forward rate and your reverse rate are the same. Yeah? I'm trying to illustrate this graphically. So we have a situation where at equilibrium, the rate of the forward direction and the rate of the reverse direction are the same, and the concentrations of species in the solution are constant. They don't change. If you remove, say, reactants from the reactant side of the equation, then the forward reaction is going to slow down, right? Relative to the reverse reaction. And so if you pull out reactants, you compress the forward rate because there simply aren't as many reactants colliding. The reverse rate stays at wherever it was just prior to the perturbation of the system because you haven't changed the concentrations of the products. Yeah? So what that means is, at that instant moment in time, when you remove the reactants, you cause the reverse rate to outpace the forward rate. What's that going to do? It's going to start making the reactants on the reactant side of the equation at a faster rate than the products are being made on the product side of the equation, yeah? So it's going to act to make more of the thing that you took away. That's one of the key characteristics of a system in equilibrium. If you change the system responds to try to compensate for that change on some. It's really a function of kinetics. You remove the reactant molecules, the system acts to drive itself in such a way as to increase their numbers again. When you remove the reactant molecules, so you had K was equal to concentration of the products, which were C to the coefficients, D to the coefficients over the concentration of reactants, and A to their coefficients, and B to their coefficients. When you pull out these reactants here from the bottom, you made the instantaneous ratio of products over reactants larger than your K EQ, right? Because you removed reactants from the denominator. And so instantaneously in time, the ratio of products to their coefficients over reactants to their coefficients was larger than what our accepted equilibrium value of K was. But what did the system do? The system went on to start pulling products out and converting them to reactants. And after it did this for a small period of time, it found a state, or it finds a state, where again, this guy is restored to its equilibrium value. Yeah? So that's one of the ways this is taught. I like to teach it from the rate perspective. You remove something, one rate slows relative to the other. A lot of people like to focus in on this K value and say that when you change that, when you shifted equilibrium, you altered the ratio of those concentrations, and so the system had to change in such a way as to restore the ratio to its KEQ value. All right, so go over all these real quick just for the sake of having done so. Same system, now you add reactants. You were at the point where the forward rate and reverse rates were equal. You add a bunch of reactants, and now you've accelerated the forward rate, right? The forward rate is now dominant over the reverse rate. Well, what that's going to do is it's going to shift the rate of action this way, such that more of the products are made, and at some point, the two rates will catch up with each other again. Notice that when we decreased the amount of reactants, we ended up with final rates that were slower than the initial rates that we started off with. When we increase the amount of reactants, as we have over here, keep overshooting it. When we increase the amount of reactants, we end up with final rates that were faster than our initial rates. We end up with final equilibrium rates that are faster than our initial equilibrium rates. You can do the same thought experiment with adding and removing products. Again, what's going to happen here is that whichever side ends up with more species colliding is going to be the dominant side, and it's going to force the reaction in the other direction, such as to create more of the species that were in deficiency. Does that make sense? Maybe? Okay. So one other thing we'll talk about. We just kind of got an idea for how equilibrium shifts when you have changes in concentrations of species. Equilibrium also shifts with temperature. And this all has to do with the fact that an increase in temperature asks the system to store energy. And there's only a handful of ways available to a system for storing energy. One of those ways was the kinetic motions. So you're asked to take on more energy, you start traveling with faster linear velocities. You start vibrating with larger vibrational amplitudes. If possible, you begin rotating with faster rotations. There's another way that a system has, another mechanism that a system has at its disposal for storing energy. Let's look at this graph for a second here. This graph shows an exothermic reaction. The reactants species are higher in energy than the products, right? And so the equation is going to look something like this. Reactants go to products plus heat. Because when the system ends up at that lower energy state, it has to release some of that energy as heat. Yeah? What that means is that your reactants are higher in energy than your products. That's the critical point here. When a system is asked to store energy, a system of matter is asked to store energy, one of the mechanisms that it can use is to simply create more of whatever molecular species was higher in energy. So you increase the temperature on a system of matter, and if it has available to it either reactant molecules or product molecules to make, it's going to start making more of whichever molecules are higher in energy. If in this, as in this case, when our reactant molecules were higher in energy, an increase in temperature is going to drive the system to make more of those high energy reactants when we move backwards. If we had an exothermic or an endothermic reaction, where the products were higher in energy than the reactants, then an increase in T is going to drive the system towards the products. This is all about systems of matter storing energy. There's some ways that you're taught to think about this in Gen Chem classes. You think of, for exothermic reactions, you think of heat as one of the products of the reaction. And so, just as when we saw that when we increased the concentration of reactants, it drove the reaction in the opposite direction. If you increase the heat here, it drives, if it's one of the heat's one of the reactants, if you increase the heat, it similarly drives the reaction in the opposite direction. So you think of heat as a reactant in that reaction. It's 9:59. I think we'll call it a day. Yeah.